Of course, today's topic, we actually got a lot. We basically call the main topic ANOVA special topics. And under this ANOVA special topics, I'm actually going to walk you through what we call the module building strategy and unbalanced design. Of course, what we've been doing before now is actually balanced design. So what happened? In a situation where we have unbalanced design, of course, I'm actually going to prove to everyone today that the conventional approach that we use, okay, will no longer be appropriate. Okay, so in the outline today, like I said, I'm going to walk you through strategies involved in model building. And not only that, I'm actually going to let you know today that we have different types of sum of squares, when it comes to unbalanced design. Okay, so I'm actually going to tell you the difference between the type 1, the type 2, and the type 3 sum of squares. And of course, I also let you know the type of sum of square that we use in a balanced design and what we use in an unbalanced design. And I'm also going to let you know today difference of, we got different softwares around. Um, I'm going to mention the popular one, like the Arrow software, the Python software, the SAS. I'm also going to give you information about, what type of sum of squared, okay, do they actually program in case you want to use R, okay, in case you want to use Python or you want to use SAS. So what type of sum of squared? Is it type 1? Is it type 2 or type 3? So all of that will be unfolded today. Okay, so we want to go into business now. So I'm basically going to start with the strategies involved in model building. Of course, you know that in any statistical, you know, when when we are trying to use statistical knowledge to answer a problem in a real life or practical situation, we always start with model. I'm going to say that again. The preliminary investigation, when we are trying to apply a statistical method, the statistical method always begin with a specification of a model. And of course, model is what I call mathematical, representation, okay, of reality. Okay, I'm going to say that again. Model is a mathematical representation of reality. Okay, now our model is always going to be in terms of notations, symbols. Of course, example is what I'm displaying to you now. Of course, you remember in class, I actually walk you through, I specify model, we specify model when we want to work with one way, ANOVA, and when we want to work with two-way ANOVA. So whatever form of ANOVA that we actually want to work on, we basically going to specify a model. Now, when you take a look at the first one here, this is a two-way ANOVA model, um, you know, with interaction. And this guy here is a three-way ANOVA model with interaction. Okay. Of course, I've walked you through this in class. Okay, so these are our model, and these are full factorial model. Okay, the full factorial model, we have a complete specification of these models. Okay, so you know, you need to notice that in the model that I've specified, we have like in the two-way ANOVA, we got one, just only one interaction. In three-way ANOVA, we have so many form of interaction. And of course, we need to be able to check in our model, we need to check the ISL order interaction time, okay, because we have the experience that it is not all the time that the higher interaction time may be significant. Okay, now the question now is when do we actually tolerate the higher interaction time in our model, and when what is the situation where we don't really tolerate that? But this is the key. If it is statistically significant, like for instance, if the higher order interaction is significant, if I'm working with two-way analysis of the variance with interaction, the moment the AB interaction is significant, then what that actually means is that we need to be able to include the main effects of A and B into our model, even though if the main effect of the main effect of factor A and the main effect of factor B is not significant, if their interaction is significant, then the main effect of A and the main effect of B need to be retained in our model. So we are retaining them in our model because their interaction is significant, even though the main effect of A, the main effect of B is not significant. So I wanted to take note of that. So that's exactly, what I'm actually trying to say here. Okay, that's what I'm trying to say. Okay, when you are working with a two-way analysis of variance, and you realize that the interaction effect is significant. Of course, the only way to know whether the interaction effect is significant is when the p-value associated with the interaction effect is less than a given level of significance. You know that, right? So, and we said if that interaction time is significant, then even though the effect of A separately, effect of B separately is not significant, okay, the effect of A and B have to be, tolerated in our model. That's exactly what I mean. And what of in a situation where it is not statistically significant, then we need to take a decision. Okay, so if that's exactly what I'm trying to say here. If the interaction time now is not statistically significant, then we're basically going to take a decision whether to pull the interaction with the residual. Okay, by removing this term from the model, because somebody is going to say, so what is the essence of keeping an interaction effect that is not significant in my model? So the moment the interaction, if it's not significant, we can actually pull that, okay, with the residuals, and pulling that with the residual, it means you're actually removing that from your model. But we have conditions under which that decision can actually be taken. So take a look at this. So we said only consider pulling a term into residual. Because don't forget, whatever you are actually pulling into residual, you are trying to tell the world the effect is not significant, because don't forget, the assumption that you have on the residual is that the expected value of the error is should be 0. And so that is so now the only condition under which we can actually do that, do you need to consider whether you have a 10 or fewer degree of freedom for residual. Okay, in ANOVA table, the degree of, we have the degree of freedom for different kind of events, for effects, and of course, residual also has its own degree of freedom. And what we're trying to say now is the moment the degree of freedom for the error, okay, for residual is actually 10 or less than 10, of course, we can do that. And not only that, that's not the only yardstick. What of in a situation, you know, we are the F statistic for the interaction is less than 2. Okay. So when the F statistic for the interaction is less than 2, of course, in the ANOVA table, the main effect as the F statistic, the interaction also have the p-value that we got at the end of the day, when of course was actually based on the F statistic. So what we're telling the world now, so when the F test, a statistic for the interaction is less than 2, we can also pull. Otherwise, do not pull. Okay, otherwise, do not pull. And of course, the recommendation above apply in situation where data are balanced. Where data are balanced is when we have a core number of participant in each group. I remember when I was walking you through an example that has to do with the type of sandwiches. Of course, you notice that in each group you got 10. I think we got eight. That's what we mean by balance. Uh, because of my internet, I think I still need to confirm again if everyone is still hearing me clearly. Is everyone still hearing me clearly? Okay, thank you so much for confirming that. Okay, now I'm going to walk you through an example now. We call that, we see we're under the model building. And as you can see in this example, you're basically going to see we have 3 factor. Okay, this is one of the factor, this another one, and of course each of the target actually have another levels. So if you take a look at what I'm actually displaying now, you're basically gonna see we got 3 factor. The researchers actually makes a team board, varying the target density. Okay, you have the target density that have 2 levels, and you have the amount of racing that have 3 levels, and also the fraction of the flash, okay, that also have 3 levels. So I wanted to take a look at what I'm actually displaying now. Okay, now this is more or less like we have 3 factor experiment. Of course, that is the data. Now, this is how to code this in R. Okay, in case some of you want to practice this. So this is the coding, okay, of this particular data set here. Okay, in R. Okay, I believe my TA is basically gonna walk you through, of course, how to go about that. Okay, now in the end, I just want to show you the results. Okay, I basically want to show you the result. Of course, as you can see in the results, it is only racing, this guy, that guy. Okay, if you want to take a look at those ones that are significant, okay, at 0.05 level of significance, you're basically going to see, even though we are considering 3 factorial experiments, it is if the highest interaction here is not significant, and some other interaction as well, not significant. Okay, if you take a look at what we have here now, based on this model, of course, if we really want to validate our model, of course, we basically going to conduct what I call regression. I mean, what I call a diagnostic testing that I told you in class, where we basically want to check whether the assumption of constant variance hold, whether the assumptions of normality hold, and of course, when you take a look at the assumptions of, when you look at the residual plot here, you basically gonna see assumptions of constant variance hold, because what the assumptions of constant variance is actually talking about is that you know, when the variance of the response have to be the same when you increase, when you go from one values of the predator to the other. And of course, when you take a look at the normal QQ plot, you can see that this is actually forming a diagonal straight line. So indicating, this is actually indicating that normality assumption also hold. Now, which means that this particular model is good. That's what it means. Okay, that was why I said residuals and normality actually look good. In a situation where the residual and the normality assumption look good, then it means we don't need any transformation. It means the model is good. But the only thing we can actually do is to remove, you know, the uh the interactions that are not significant. If you go back into the model, okay, I'm actually going to remove all the significant or insignificant terms. When I remove that or insignificant terms, so what I'm going to do, I'm going to rerun the model again. And that's exactly what I'm doing here. So which means I've already removed all two-way interactions. I've already removed all those ones that are not significant, and I decided to rerun the model. And of course, rerunning the model, of course, the those terms that were significant initially were also significant again. Take a look at that. Take a look at them. So what is this suggesting to me? So this is actually suggesting to me that this is what I should actually focus on. Okay, so take a look at that. Okay, so that is just the model strategy. So the takeaway from the model strategy is just to be able to tell us how we can actually remove insignificant effects in a model. And I think I also told you the other time, you don't just remove them, you're also going to pay attention to the F value. You remember the other time, I'm going to take you back. I mentioned that here. Take a look at that. Okay, I said the only reason, okay, I said when the F test statistic for the interaction, okay, is less than 2, and not only that, if the degree of freedom for a residual is 10 or 10, less or equal to 10. So, and as you can see, when I force run this, you're basically going to see the insignificant one. Oh my God, the insignificant one actually have the F value of less than 2. Do you see that? You can see that. So which means we're actually following the rule, the module strategy now, module building strategy now. That's actually telling us, okay, to basically remove. We're not just removing insignificant terms, but we also put into consideration, those time, whose F value is less than 2. And as you can see, the one with the F value less than 2 is the one we actually remove. And not only that, there's something I wanted to pay attention to here. Oh my God, the residual, the degree of freedom for residual is actually 4. And what did they tell us? They tell us the condition to remove. Okay, so when the degree of freedom for residual is 10 or less than 10, so which means this particular result here, we basically justify, we've already justified, excluding some terms. We're not just excluding some terms based on the fact that they are insignificant, but we also put into consideration, that the F value is less than 2. Okay, and not only that, the degree of freedom is actually less than 10. Okay, so take a look at that. Okay, so that's all about model building strategy. Give me 1 second. I think a chat actually came in. Somebody said, why didn't we consider three-way international time in this case? Oh, I think that is what I just explained, when you look at the three-way interaction that we did initially, it is not all, look, if you take a look at all these times, they are not significant. And not only that, as you can see in their p-value, not only that, the f value is actually less than 2. Look at that. The f value is less than 2. Did you see their f value is less than 2? And not only that, the degree of freedom for a residual is also less than 10. I want to believe whether, whether the person that chats with me now, or maybe if I've answered your question about the reason why. Okay, thank you too. Let me, I'm still reading my search on my chat. Somebody said, um, okay, why didn't we? Okay, I think I've answered that one. Somebody also said that there are times when something that was significant prior to the moving factor becomes insignificant. Actually, what we going when we're using here, we have a threshold. We got a threshold that we are actually and even though there may be some prior knowledge or prior information before you go into experimentation, maybe when you are reviewing your the research article, literature, and probably that some effects may not be significant in advance. But you know what? I don't also rule that out. But this is what I'm presented to you today is how you can actually use statistical approach to decide on what to remove or what not to remove, even though I know you may be guided by something outside statistical framework, but what I'm presenting to you is what is tenable. We know what the statistical way of doing that. Okay, so that is I've just achieved the objective number one for today. Okay, I want to go into objective number two. And I need everyone to focus attention on this area because in research, of course, we normally come across unbalanced design. All what we've been talking about, of course, even in the last example that I just cited, are actually based on a balanced design. So I want to welcome you into another objective of the day that we call unbalanced design. Okay, so in the unbalanced design, we have reasons. And when I say unbalanced design, I mean in different group, you have unequal number of observation. Okay, you got unequal number of observations, so they are not equal replicates. That is what I mean. And of course, we got several reasons why that can happen. Okay, we live in a stochastic environment, we live in a probability space, and of course, we got reasons why we could have unbalanced data. Okay, number one, I said the balance designs produce unbalanced data when something goes wrong. We live in a world of surprises, right? What if in a situation you're working on plant and certain plant die? What if you are working with a particular machinery and that is producing something and there's a breakdown, or the shipment of raw materials don't come on time? I remember when we are faced with a supply chain issue. So what about in medical field where we actually are using some volunteers, probably in a clinical trial, and there's where we could have a situation where some of them may drop out of the study, and we could have situation where subject could get sick. Okay, and not only that, don't forget, some treatment may actually be more expensive or more difficult to run than others. Okay, so and don't forget we're limited by budget, and of course, so we could have a situation where we're going to have more in one group than in the other group. And of course, at times, some treatment combination maybe of a particular interest, and especially if they are new, and the experimenter can decide to have more sample from them, compared to the others. Okay, so I need you to again to confirm if you're still hearing me clearly. Is everyone still hearing me clearly? Okay, thank you so much. Thank you for confirming that. In case you want to ask question at any time, of course, you let me know or you can chat with me. Okay, thank you so much. Now, you know the reason why we have unbalanced data. Okay, from that reason now, I'm actually going to show you a layout. You know, when we're talking about unbalance. Excuse me. I'm actually going to start from a balance scenario. Okay, maybe I have 6 groups, right? And of course, when you take a look at the first one here, so this is equal replicate. The number that I have in each of the group is the same. So this is balanced data. Okay, but what if in a situation where take a look at the second one, this is an unbalance. What is making this unbalance is the fact that n equal to 6. Okay, nobody knows what happened. Okay, so take a look at that. It could be one of those reasons that I just talked about. Now, what about missing cell? Okay, we could have a situation where one or two group may be completely missing. Okay, so I'm just trying to tell you, to show you some types of data that we have. Okay, now the next thing I want to talk about now is this. So which means I've just walked you through different kinds of data. So we want to focus on unbalanced data now. And of course, in an unbalanced data, of course, I just show you we got 2 types of them. Okay. The second one, this one, and this guy here. So those are the types of unbalance. A data can be unbalanced if you have different items in different group, and of course, or it may be unbalanced if a particular group is completely is missing. Okay, so that was what I was trying to talk about here. Okay, now let me tell you this. When we actually working with the balance data, okay, I want to tell you a balanced data actually have advantages over the unbalance. I just wanted to know that. The balanced data have what I call nice statistical property. So what do I mean by that nice statistical property? I'm actually going to let you know now. You know, when you talk about the orthogonality, you remember in class, when I was teaching contrast. Okay, I said that I think I gave a condition under which contrasts are orthogonal, and of course, when contrasts are orthogonal, you know what that means. It means the contrasts are independent. Now, when you have a balanced data, okay, and you are working with maybe 2-way or 3-way analysis of variance, okay, the main effect, the interaction effect, whatever effect that you basically want to test, they are orthogonal. Orthogonal means they are independent. Independent means, when you actually figure out one, does not really depend on the other one. That's what we mean. That's what we mean by orthogonality. Okay, so what we're trying to talk about now, okay, that we will be able to compute the sum of square in our Nova table that does not depend on the other term. Okay, so all balanced data has this property of orthogonality. The orthogonality actually means independence. Does that make sense? Now, I want to tell you this. You know, um, when we are working with one-way analysis of variance, okay, unbalanced data is not an issue at all. I'm going to say that again. When we're working with one-way analysis of variance, unbalanced data does not pose any threats. Okay, but when you are working from two-way analysis of variance and beyond, I'm going to say that again. When you are working with two-way analysis of variance and beyond, okay, then when you use technique, when you use ANOVA technique that you use for balanced data, when you use that on unbalanced data, you're basically going to mislead the world. I'm going to say that again. Oh my God. I'm going to say this again. When I'm working with one way analysis of variance, whether balanced or unbalanced data, there's no issue. But we normally experience issue when we are working with two-way and beyond. Maybe I'm working with two-way ANOVA, three-way ANOVA, four-way ANOVA, and so on like that. Of course, the result I'm actually gonna get, with the balanced data will be different from what I'm gonna get with the unbalanced. And I said, because of this, I actually want to present to you to the type of sum of squared. Now, let me tell you this. You know, um, the idea behind analysis of variance is to split the sources of variation into various components. And the only way you can do that is to use a technique of ANOVA that we call sum of square. Okay? Now, let me tell you this. For balanced data, so I'm presenting to you today that we have a type 1, we have a type 2, we have a type 3 sum of square. But situation where your data is balanced, the type 1 sum of square will be the same as type 2 sum of square will be the same as type 3 sum of square. But situation, oh my God, situation whereby your data is unbalanced, then the type 1, type 2, type 3 sum of square will no longer be equivalent. And you may want to ask, what type of sum of square have we used before in this course? Of course, we've been focusing on type 1 sum of square. Okay, so today I'm actually going to tell you what is the difference between the type 1 sum of squared, the type 2 sum of squared, and the type 3 sum of squared. They are not the same. Okay, now let me just tell you before I go, the recommendation is that when you have unbalanced data, the statistician will actually prefer using type 2 and type 3. Okay, type 2, if interaction is not involved. Type 3, if interaction is involved. But when we have a balanced data, oh my God, we can use any of that, because for balanced data, type 1, type 2, type 3 will give you the same results. But for unbalance, and you are working with two-way ANOVA and beyond, oh my God, type 1, type 2, type 3 sum of squared, we give different results. Okay, I just wanted to take notes of that. Okay, now I'm actually gonna first walk you through the understanding of the sum of square, the way sum of square work. And I'm going to start with the two-way ANOVA. I told you the issue, when you're talking about unbalanced design, unbalance is an issue if you're considering two-way analysis and beyond. Okay. But for one way, there's no problem with either balance or with unbalance. There's no problem. But with two-way and above, oh my God, we're going to have problem with our balance. And that is the reason why I basically want to let you know the type of sum of square you're basically going to use that will not mislead. But I first want to walk you through how, the sum of square actually work. Okay, now take a look at this guy now. Okay, I want to talk about the sum of square from two-way ANOVA with the main fed and interaction. Of course, there's always going to be an intercept time, right? Then I'm going to be a main effect A, main effect B, and the interaction. If I'm not interested in the interaction, that means I'm focusing on this guy. You can see there's no A, B here, right? Now, do you know, if I look at if I put this guy into consideration and this guy into consideration, that will enable me to, determine the influence of interaction. I think you know that. Take a look at what I'm doing now. For instance, this guy is trying to tell me, I want to focus on interaction. But given that I've already investigated main effect A and main effect B, I'm going to say that again. I want to focus on the interaction now. putting into consideration main effect A and B. Of course, what I'm trying to tell you now, the mathematical difference between when I consider model with interaction and without interaction, will basically give me the SSAB. The SSAB here, the SS interaction here means I'm adjusting for AB, putting into consideration the main effect of A, the main effect of B. And you know what? Do you know you can also do that by trying to look at the difference between the sum of squared. Oh my God, the sum of square residual that are actually called unexplained variation when you put into consideration model without interaction and model with interaction. What I'm trying to tell you now, this guy here is a sum of squared residual when when you don't consider interaction. And this guy is the sum of square residual when you consider interaction. Do you know when you subtract the two variation? Oh my God, you're basically going to have the SS int AB, the sum of square interaction, putting into consideration the main effect. And that was why I actually said, yeah, I said that represents a sum of square sum of square for interaction adjusted for the main effect in the model. Now, I'm going to walk you to, let's look at the arrow code now. So what is the implication of that? I wanted to take a look at the first one here. The two arrow code here, the two arrow output here is just basically talking about two-way ANOVA with interaction and the two-way ANOVA without interaction. So let's say, you remember the example that I used in class where we are trying to use a sandwich data, where we are trying to look at the effect of type of sandwiches and the types of bread on on ants. Okay. Now the first one actually talking about the interaction. The second one is talking about without interaction. Oh my God, when I consider with interaction, take a look at the p-value associated with the interaction in that model is not significant. And maybe that was the reason why we focus on one without interaction. But you know what? There's something I want to, because I want to explain how to adjust, how to actually compute the sum of square for interaction, adjusting for the main effect. You know what you can do? Take a look at that. I want to get SSAB now. I want to get the sum of square interaction, adjusting for the main effect of A and the main effect of B. I said I'm actually going to use this formula, or I use this formula. Do you know if I want to use the formula now, oh my God, I'm actually going to go back here. I'm looking at if I want to go by residual, I'm actually going to use the residual here and the residual here. Take a look at that. When I subtract the residual, what happened? Oh my God. When I subtract the residual, that will give you the sum of square interaction 76. And let us see, is that what we have in the table? Oh my God. Take a look at that. Is that not beautiful? Take a look at that. So that is the same thing as that 76, which is the sum of square interaction in the table. Now, if you want to look at it from, using this guy, okay, all what you just need to do is to consider add effect that is not, this is what I mean. Oh my God, you see that guy and you see this guy. What is the difference between them? There's this guy here, there's this guy here, there's this guy here, there's this guy here, then the difference is 76. That is another way to figure out sum of square for interaction, after you've already adjusted for the main effects of A and B. So that is exactly what I'm doing here. You can see, each of that actually gives 76. Okay, so this is if I want to go further, like this is for the AB. Okay, well, this is like the first one is trying to tell me, okay, I want to figure out the sum of square interaction AB after adjusting for a main effect of A, main effect of B. This is like getting the sum of square for main effect A after adjusting for main effect B and adjusting for interaction. So the same thing also goes like that. Okay, now I want to focus now. I want to go into what is the difference between the type 1 sum of squared, type 2 sum of squared, and type 3 sum of squared. Now I'm basically going to explain to you now so that you basically going to know the difference between the two, between the three. Now I'm going to tell you now. When you are working with balance data, the type 1 sum of square we give is going to be the same as type 2 and type 3. They're all going to have the same result. But if you're talking about unbalanced, they will not be the same. So which means the type 1 sum of square that you use on unbalanced data, you cannot use it on unbalanced data. I'm going to say that again. The appropriate type, sum of square you can use for the balanced data is type 1. So which means the one we've been using in class, that is type 1 sum of square. But if you are working with unbalanced data, you cannot use type 1 sum of square. And in this lecture, I'm basically going to demonstrate to you the reason why you cannot do that. Okay, the reason why you cannot do that is because, the total, when you are working with a two-way ANOVA, okay, and you have factor A, factor B, and factor A, B, okay. Now I want to put it to you that the one you call factor A, that is the one that we have the maximum amount of variations. But the factor B, okay, the remaining, when you consider maximum variation for factor A, the remaining variation, the maximum of that will now be assigned to B. Okay. Now, the moment you now account for variation in B, the remaining, okay, the maximum of the remaining is the one that you're going to assign to interaction. Then the outstanding one will now be assigned to residual, which means order do matter when you're talking about type 1 sum of square. Okay, so that is what I'm trying to explain here. This should not be used for unbalanced data, okay, because it's basically going to assign more variation to the the first factor. Okay, now I'm actually going to show you an example now. Like if you're working with balance, whether type 1, type 2, or whatever, they're going to remain the same. Now take a look at this example where I'm looking at the effect of gender and education, okay, on salary. The gender has 2 level, education has 2 level, degree or no degree. We're looking at the effect of that, right? Okay, this is the the bus plots of that. As you can see, of course, you can see differences, okay, for the between female and male with degree or no degree. But let me first show you the results here, and you basically going to understand what I'm trying to say. Take a look at this. I want you to focus on this guy. What did I use as factor A here? Gender. I use gender as factor A, and I use education as factor B. Okay. Now, because the data set is balanced, what if I switch that? If I now use education as factor A and I use gender as factor B, what will happen? Does that going to change things? I'm going to do that now. Okay. Oh my God. Take a look at this guy. Take a look at this guy. Do I have a different result for balance when I actually take a look at here? I use gender as factor A, but right here I use education as factor A. But because I'm working with a balanced data, okay, the sum of square for gender here is still the same as the sum of square for gender here. The sum of square for education is still the same as sum of square for education. There's not going to be any difference at all because I'm working with the balance. When I use type 1 sum of squared for balance, okay, whether I use gender as factor A or I use education as factor A, it doesn't matter because the fact that with the balanced data, of course, the result is not going to change. Okay, the result is not going to change. But and that was why I'm making this conclusion. everything looks so good. And of course, in R, okay, when you see this guy, this is what we normally use, AOV, lowercase ANOVA, all those ones are for type 1 sum of square. Anytime you're using that code, remember that you're dealing with a type 1 sum of square. Okay, but you know what? I want us to see now. We basically want to look at the performance of type 1 sum of squared when it comes to unbalance. Oh my God, some data are not available. Okay, take a look at this. Is complete. This is not. Look at that. This is not complete, and this is not also complete, right? Now we have reframed that to look like an unbalanced data now. Oh my God, we have unbalanced data now. Okay, now let us look at the behavior of type 1 sum of squared. Now, in the behavior of type 1 sum of squared, focus on the interaction now. When I use gender first, when I use gender as factor A, and I use education as factor B. Now, what now happen when I switch that? Now, take a look at that. This is the first one, right? When I use gender as factor A, and education as factor B, but here when I switch it, let us see whether we're going to have the same result. The sum of square for gender, yes, is 0.3, but the sum of square for gender, yeah, oh my God, they are not the same. That is what I'm talking about. That's exactly what I'm talking about. So situation whereby you have unbalanced data, the type 1 sum of square will not give the same results. Will not. I think I'm actually going to stop here today, and I need someone to ask me a question. We're going to continue from where we stop next week. Is there any question on what I've just presented today? Is there any question? Is there any question? Okay, the takeaway from today is to just tell the world that the type 1 sum of square that you always use, always appropriate when your ANOVA data is balanced. But if it is not, it's basically going to give different results. So I think I've demonstrated that to you today, that for balanced data, the type 1 sum of square work great, it's going to be consistent, but for unbalanced, it's not going to be consistent at all. And we're basically going to consider type 2 or type 3. So in my next lecture, okay, I'm going to walk you through type 2 and type 3 sum of square. So which means type 2 and type 3 sum of square is what should be used for unbalanced data. Okay, so where to use type 2, okay, when interaction is not involved, and where to use type 3 is when interaction is involved, okay, for unbalanced data. Okay, on Friday, of course, be reminded that we're going to have our test. Okay, I believe you're already preparing for that. I'm actually going to see you in class on Friday. Make sure you stay safe. There's a winter storm or alert in place, so make sure you stay safe. Okay, stay safe, and I'm basically going to see you on Friday. Okay, bye for now, everyone.